Right, okay. So do you know yesterday I introduced you to this concept of the standard normal distribution, which I just think is unnecessarily complicated, because all that standard normal distribution does is it says, if you know the probability, I'll tell you how far away from the mean it is. Okay? And it's useless because we've got calculators which will do all the inverse normal calculations for us. Well, it's useless unless we don't know the mean or we don't know the standard deviation. Because in order to use our calculators, we have to enter the mean and standard deviation in order for it to work out anything for us, whether it's a probability or whether in an inverse situation it's working out the value that gives you that probability. So this is the only place really where these days the standard normal distribution is of use. And actually this is such a contrived topic because you can't work out the standard deviation without working out the mean. You know, the formula for the standard deviation involves the mean, so it's just a way of trying to get you to do some sums, all right? So we'll embrace it, So I've got this random variable that is normally distributed, and I don't know the mean. I don't know the mean. Right, we need a title, don't we? So this is finding mu for using z values. Remember, z values are the number of standard deviations away from the mean. So now the probability that x is greater than 20 is 0.2. Right, so straight away I know that because the area under this graph is 1, and therefore the area to the right of the mean is a half, I know 20 is bigger than the mean. It'll be, I don't know, somewhere here. But I can't use my calculator because I don't know the mean. The calculator insists you type in the standard deviation and you type in the mean, and then it'll tell you all you need to know. So here's what I'm going to do. I'm going to turn to page 34 in my formula book and see what it tells me about how many standard deviations away from the mean you go to get a probability of 0.2. So page 34 in the look at this. Just. So I'm switching to red ink because I'm now looking up a z value. Remember, a z value. I'm switching to green ink. I've lost my red pen. The z value is how many standard deviations away from the mean you are. Page 34. So I'm looking for a probability of 0.2. So that's the P column. So I hope you can see it's 0.8416. And that would work at this end if it had been the probability x is less than 20 is 0.2. It would have worked that way, except it would have been minus 0.8416. So I know that 20 is that many standard deviations above the mean. So I know that 20 is the mean plus 0.8416 standard deviations. That's what that value tells me. It tells me how many standard deviations away from the mean 20 is. And so what I can do is a little bit of arithmetic to work out the value of the mean. Hoping that I get an answer less than 20 because I've already know that 20 is. Are you ready for the non-calculator bit? quite a lot going on there. So both sides. Don't worry if you don't finish, just get as far as you can.
So how did you...
Take that one as well. Yes, sorry.
How did you know that 20 was above the mean?
Because the probability of greater than 20 was 0.2. So the probability of being greater than the mean is 0.5.
Right, okay.
So 0.2 is less than 0.5, so I knew it was that way. How do I know this is a normal distribution question? That's the so I'm going to shoot. I'm hoping you get 17.5, 3 significant figures. Now I could not do this without a picture, okay? And you know, you might be, well, many of you are going to be better mathematicians than me, certainly make far less mistakes than me, but I would strongly encourage you to do a picture. So go on, see if you can do a picture for this problem. This time, what we've got missing is the standard deviation. So see if you can just draw me the curve, and I'm hoping on that x-axis, that bottom axis, you'll be able to label 50 and 46 and shade a region for me. Remember, with normal distribution, whether it's less than or less than or equal to, we don't worry about it. So I'm hoping your sketch looks like that. So I'm hoping you're looking in the tables for a probability of 0.2119. And I hope you're frustrated because it isn't there. It isn't there. What can we do? Well, don't forget that these tables show us the probabilities for this standard normal distribution, which is this pretend normal distribution that has a mean of 0 and a standard deviation of 1. So what I can do is actually get the answer from my calculator, and this means that the tables are actually completely useless because I could have found the previous answer from my calculator and all the other z values we used yesterday from my calculator. So here's what I need to do. I need to go to my calculator and go to distribution and normal and inverse, because we know the probability and we want to work out the value. And I just type in a standard deviation of 1 and a mean of 0. That's how I set up my calculator to give me the values that the tables give me, except they don't give me for all the probabilities. And we saw questions yesterday that said using the percentage table. So if it says that, it'll be a probability that's in the table. So in my case, this is a left tail problem, and my probability is 0.2119. that gives me the Z value. And if I look at the table, the Z values are rounded to 4 decimal places. So I'm going to round that to 4 decimal places. So sorry, I should have done that in black because that's real. What I'm now saying is that 40 is 0.778 standard deviations below the mean. So what that means is that 40 is equal to 50 minus 0.7998 standard deviations. Standard deviation in this problem is what I want to work out. So go on, see if you can work it out.
Wait, why did you put 40?
Why did I put? Oh, it's 46. That's just my bad handwriting, isn't it? Again, sorry, being lazy. Right, so they've, don't know why, they've rounded to 2 decimal places, there we go. Anyway, we get 5-ish. Now, this is where I need you to promise me that you'll do some practice. We haven't got time for it now because I said I really want to get to a nice natural end by the end of tomorrow's lesson. But you've got 2 questions there that practice finding the mean and 2 that practice finding standard deviation. Okay? Now, I like questions where you're asked to find the mean. And I really like questions where you're asked to find the standard deviation. Guess what's coming? What if I don't know either? What if I don't know either? Well, I'm sort of hoping you can see what's happening here. This is a simultaneous equation question, isn't it? Because given this bit of information, I'm going to get one equation involving the mean and the standard deviation. And given this bit of information, I'm going to get another equation using the mean and standard deviation. And because one bit of information is a greater than statement and one is a less than statement, I can probably put both of these on one diagram. So go on, see if you can sketch the diagram for me. In both cases, these probabilities are less than a half. So I know 35 is greater than the mean and 15 is less than the mean. So it makes my diagram nice and easy to draw. One of those values you will find in the tables, one you will not. But of course you can look up them both on your calculator if you can't be bothered to turn to page 34. And I'm sure Lily and Jodie, that's why you didn't bring your formula book, because you knew you were going to be able to do it without it.
Right, I've reached the end of my...
My patience with it. COVID is officially over. I'm now going. See if you can look up your Z values. As I said, this one you'll find in the tables. This one you'll have to use your calculator, but you can use your calculator for both. You don't have to use the tables. Remember to switch, remember to make sure you record whether it's a left or a right tail. All the Z values in the table are positive, so you've just got to remember if it's a value below the mean, then you have to make it negative. But the calculator deals with that problem for us, so yet more reason to use your calculator. I'm told that 15 is 1.0498 standard deviations below the mean. So 15 is the mean minus 1.0498 standard deviations. 35 is 1.96 standard deviations above the mean, so it's the mean plus 1.96 standard deviations. And I'm sure you could solve those equations using a whole range of methods. Don't forget, you've got the option, and the examiner got back to me and confirmed that this is still okay. You've got the option of solving that simultaneously. The simultaneous equation function only knows about x and y. I've got mu and sigma. But I'm going to enter those calculations. So that's going to be 1 mu and minus 1.0498 sigma equals 15. And in the second equation, 1 mu plus 1.96 sigma equals 35. So it's expecting it in some x's plus some y's equal a number. I've had to sort of fiddle that a bit, but it's going to give me an x value, which will be my mu value, my mean, and a y value, which is my standard deviation.
It doesn't draw tables on it. Oh, I know that's cool. Never mind. Oh. I'm trying to move.
And I'm going to round those to 3 significant figures. And I just need to be slightly careful because there's no context. So it's not 22 centimetres or, sometimes there are contexts, aren't there? This one there's no context. I'm just going to double check that. I've got that one right. Again, I need you to promise me, maybe not all of those. I mean, you could just do 1, 3 and 5 or 2, 4 and 6. That way you do 1 that finds a mean. Actually, no, sorry. You'd have to do 1, 2, 5 or 3, 4, 6. Just do 1 where you find the mean, 1 where you find the standard deviation, 1 where you find both using simultaneous equations. And we are halfway through the lesson, which is good, because that's halfway through the things I wanted to teach you. Are you okay? Are you using simultaneous equations?
Mm-hmm.
So you...
5 per x.
No, that's right. So that needs to be minus 1. Are you doing this one or this one?
That's the one that you're putting at now.
So that's you need to see your y value needs to be minus 1.0498. And then that's 1.96. And then 35. And then you press equals, just press equals. Oh, why have you got to plus? Oh no, yeah, that's the same. If you round that to 3 significant figures. Yeah, you okay? Good. Right. Okay. So the last thing I want to cover today is using the normal distribution to approximate the binomial distribution. This is another thing which has been rendered completely redundant by our calculators. But in the old days, when we used to look up binomial probabilities in tables, they didn't go any further than n is 50. So if you were doing something more than 50 times, you couldn't work out the binomial probabilities. These days, n can be whatever we want. So this is yet another place where they are just expecting us to solve some problems and do some sums. Now, I've spent many an hour stood at the court side watching young men play tennis. Mine sounds a bit creepy, sorry. My son was a tennis player, so that's why I do. So let's just say that I decide, Mr. Godber and I are going to take on Pat and James, two people I saw watch tennis for many hours at doubles. Although Mr. Godber and I are, relatively fit, particularly for our age, I suspect the probability of me and him winning against the dynamic duo would be fairly low. So if we played 10 games and we did that every weekend for a year, we played 10 games of tennis, I mean, we'd be shattered. I suspect that if we counted how many times Godber and me won and plotted, it would probably be something like that, wouldn't it? You know, the probability of us winning a game would be very, very low. If, however, I decided on my own to take them both on at basketball, I've played a little bit of basketball in my time, I think it might be slightly different. I think if we played 10 games of basketball each weekend and counted how many I won, I think I'd take them to school. Time will tell, I don't know. Time will tell, maybe we'll get a chance. If, however, we decided to do a game that neither of us had played before and we were both perfectly evenly matched at, so I don't know, tiddlywinks. So we played 10 games of tiddlywinks. So the probability of us winning is pretty much 50-50. We'd probably see a graph like that, wouldn't we? You know, I would, on average, probably win 5 of those games. Some weeks I'd have a blinder and win them all. Some weeks I'd not do very well and win none, but you know, we would probably see that. So we get binomial probability distributions that come in all different shapes and sizes, depending on the probability of success. If there's a low probability of success, then you don't get many successes. If there's a high probability of success, then you get lots of successes. And if it's 50-50, you get something vaguely symmetrical, which of course is what the normal distribution always looks like. So what we can do is we can say, right, I can use the normal distribution, which in the old days, there's no idea about the number of times you're doing it with the normal. You've just got a set of data and you just need to know the mean and the standard deviation. The number of values you have is irrelevant. I can model the binomial distribution as a normal distribution if P, the probability of success, is close to 0.5. So I can take a variable and say, actually, I can estimate this using the normal distribution if the probability in whatever it is we're doing is close to a half. There's another issue. And that is, if you're not doing something very many times, actually this graph is not, it's just a shortcut, isn't it? With the binomial, we're actually dealing with discrete data. So what you've got actually are the probabilities of all the possible results. So here's a situation where we're doing something 14 times. So there are 15 possible results. That chunky graph doesn't look very normal. If, however, you're doing something lots of times, then the chunks become a bit less chunky. So the other thing you need in order to be able to use the normal distribution as an approximate for the binomial is you need n to be large. And large is a very vague term, isn't it? So in questions, it will always say use an appropriate approximation. You'll be told that, right, n is large enough, n is large enough. There's another problem. The binomial is discrete data, whereas the normal distribution is continuous data. So we've got that problem to address. We'll address that in a minute. And the final problem we have is that when we describe the binomial, our parameters are the number of times we're doing whatever we're doing, and each time we do it, the probability of success. With the normal distribution, it's the mean and the standard deviation, or the variance, the standard deviation squared. So what are they? Well, hopefully you already remember that with a binomial distribution, the peak occurs at n times p. So if chance of me beating James and Pat is 1/10, and we play each other 10 times, I expect to win 1/10 times 10 once. So this is n times p. So if you know n and you know p, we can approximate it as a normal distribution where the mean is 7. What about the variance, the standard deviation squared? Well, I'm just going to tell you this. The good news is it's in the formula book. That is n times p times 1 minus p. So in my tennis example, that would be 10 times 0.1 times 0.9. In this case, it would be, except you couldn't do it in my tennis example because my tennis example doesn't have probability close to a half. In this case, it would be 14 times 0.5 times 0.5. That gives you the variance. So you must remember to square root this to get the standard deviation. And if you look on page, that's page 8 in the formula book, under discrete distributions, it gives you the mean and the variance for a binomial distribution. The mean is np and the variance is np times 1 minus p. So you don't need to remember those two things. So there's quite a lot going on here. We need p to be close to a half, we need n to be large. We've got a way of working out the mean and standard deviation, or the variance, which we square root to get the standard deviation. We still haven't dealt with this problem. So let's look at an example. So a binomial random variable. So this is, well, we don't know what it is, but whatever it is, we're doing it 150 times, and every time we do it, the chance we succeed is 0.48, almost a half, almost a half. So it looks like we're doing pretty well in terms of those two criteria, and we're told to use the normal distribution to approximate it. And they've even done the calculation for us. So they've done 150 times 0.48 to get 72. And they've done 150 times 0.48 times 0.52 to get the variance. And the answer to that is 6.12 squared. So they've even square rooted it for us and told us the standard deviation is 6.12. So here we are with our normal distribution. And we are asked for the probability that x is less than 70. The mean is 72. So I know my answer is going to be it's going to be less than half. This is the tricky bit, all right? If you didn't think the rest of it was tricky, this is the tricky bit. 70 is a discrete number. So we're doing something 150 times and we're saying what's the probability that we win less than 70 times? When I translate that into continuous data, I've got to think, right, what is the biggest value that would still be rounded to 70? I want to know the probability of less than 70, so I've got to include any value that will be rounded to 70. So what I'm going to type in on my calculator when I look for the probability is actually 70.5, because I know that everything below that will be rounded to 70. We call this a correction or a continuity correction. You've got to adjust your upper and lower according to the whole discrete continuous thing. And it's made more complicated by the fact that we've got sometimes the line there and sometimes the line not there. So, to the calculator, we are dealing with a normal distribution with a mean of 72 and a standard deviation of 6.12. and we're looking for a probability. So we're not using inverse, we're using the normal, cumulative normal distribution page on our calculator. And because I'm looking for a probability, I need a lower and an upper. Lower is nice and easy, isn't it? You haven't got to worry about the whole 4 standard deviations thing. So, 0 then. So that's the probability in this normal distribution of getting less than 70.5, which gives us an estimate of the probability in the binomial distribution of winning or succeeding less than or equal to 70 times. Let's look at the second part of that question. This is discrete data. And I'm not normally pleased that I make my mistakes, but remember I made a mistake yesterday that Charlie corrected. I had a question like this with the normal distribution, and I used lower 80, upper 90, which of course was wrong, because if x is a discrete variable, it can only be whole numbers. If it's got to be less than 90, what we're actually saying is that that's the same as this. And so when I convert that into continuous data, I'm actually going to be looking between 79.5 and 89.5. I have to say, I planned this on Monday night, and no, it was Tuesday night because it was half time in football, and I just getting the whole equal to, not equal to thing clear in my head, I found really hard. So I resolved that what I would always do, because it's binomial, everything's discrete, I would always convert what it was into a equal to inequality, because this is error intervals, isn't it? This is back to GCSE. So go on, just check, back to your calculator. We're looking for the probability of between 79.5 and 89.5. Yes.
What's the need of the binomial bit then?
So what we're doing is we are wanting to work out, we're trying to work out probabilities that relate to this binomial.
Yeah.
And to do it, we're using the normal as an approximation of it. So at the end of the day, the answer that we're getting is an answer to this binomial question. What's the chance that with 150 goes and the probability of winning being 0.48, you win somewhere between 80 and 89 times. So we're the good news is that you can always check it, because the calculator will give you the actual answer to this by going into binomial mode. So you're okay, you know, in terms of being able to check your answer. So you get 0.1081. What was your question?
Neil, done.
You're done. I wanted to double check because I don't believe you've done that whole test. You've got 10 minutes left, okay? 10 minutes left. Yeah. Yeah, go sure. Yeah. So let's do a question where it asks us to compare the actual answer that you get from the binomial with the estimated answer for the normal. I don't know whether that will help clarify it in your mind. Yes, sorry, is this one? There we go.
I feel like this just seems a bit silly.
It's pointless, yes, it is pointless, but it's well, yeah, it's problem solving, isn't it? And you know, I think demonstrating that you can solve problems is what A-level maths is all about. So I can get my calculator into binomial cumulative mode, or B, C, D, or C, B, I forget which way it is, and just type in lower and upper of 50. So I type in number of trials is 50, probability is 0.55, lower and upper is 50, it gives me the probability of 50. So that's in binomial mode. Binomial mode. What I can also do though is say, right, because n is quite large and the probability is quite close to a half, I can estimate that probability using the normal distribution. So I'm going to calculate the parameters for the normal distribution. This is n times p, which is 44. I'd already worked that out because I always like to work out where my peak is going to be with a binomial question. And then the variance, which is 44 times 0.55 times 1 minus that, which is 0.45, is 10.89. And so the standard deviation is the square root of that. And I'm not going to work it out because the calculator in stats mode will allow me just to type that in. Now, I want the probability that x is 50. So the question is, because of the whole discrete continuous thing, what am I going to type in normal mode as my lower and upper? What do you reckon, Charlie? What am I going to type in as my lower and upper? Brilliant. So what I need to have as my lower and upper are the values which round to 50. Because 50 is a whole number discrete value. And when I switch to the continuous world, I just need to make sure I include all the values which would round. And I know 50.5 would round up to 50.1. That's the limit, isn't it? We always say that. So that gives me the probability that x is 50 according to the normal distribution. Yes.
Where are the? How do you know what P is and what is?
So P is in binomial, N is the number of times you're doing it. So a random sample of 80 bulbs. So in this case, our games of tennis aren't games of tennis, they're planting bulbs. And they do that 80 times. Each time they plant it, the probability of success that it comes up with yellow flowers in this case is 0.55. So that's where, I had to sort of extract those from the question.
Okay.
Now, the percentage error, you've got a couple of ways of working it out. You can just you need to have the correct answer on the bottom. So that's going to be this answer. So you're going to put the binomial answer on the bottom. You can either put the normal answer on the top, and that'll be your multiplier, or you can work out the difference, put the difference on the top, which will actually give you the exact percentage. The key, though, is that you put the correct answer on the bottom, and that gives you your percentage error. So
Was I supposed to do it in
the
the
top,
normal, just the second one?
yes, the second one between, you should have typed in this and the square root of that as your parameters, and then you're looking between 49.5 and 50.5. Let me show you what I get. So I'm still in normal mode, so now I sort of disagree with the book here, because the book goes to more than 4 decimal places. So I'm going to go to 4 decimal places with that one. They're going to come out and go into binomial. Right there? Yes, in the maths office. There's a sign saying, so yours are in the taller box, underside saying paper 3. Make sure you get paper 3s, because there are 2s and 1s there. Binomial, B, C, D. Yes? Oh, I done that wrong. Oh, I do 44? I should have done 80. Is that what I did wrong? Oh yeah, sorry. Thank you. So it's 80 times 0.55 times 0.45, isn't it? Thank you. So that I get 19.8. Is that what you get? Yeah, thank you guys. Okay. Right, so that's wrong. Let me, rather than me babble away, let me show you I got a slightly different answer. They went to, no, hang on, that's not the right answer, is it? Oh, it's this one, sorry. Yeah, so they, for some reason, went to 5 decimal places. So I think mine came out slightly different, but I think mine's absolutely fine. Something along those lines. So that's your normal probability. That's the actual probability, the binomial one. So it's the difference of those two over the correct one gives you your percentage. And it's not far off. It's not far off. And now I am very happy. I see next time I teach A-level is with my other group period 1 tomorrow. So I'm very happy I can't let you take them home. If you wanted to hang on to the book because you've got 3 periods today and you want to do a bit of it there, then that's absolutely fine. Books are here. If you want, or if you want to do it after school today,